Hi everyone, welcome. Nice to see you. Let's all take a nice deep sigh of relief as we get ready to discuss aging, aging here and there. Aging everywhere. Congratulations, we made it all the way to lecture 8. Today we will discuss longevity reflected in your plate. There's calories and feedback loops that are beautiful to watch. And today we'll study them a lot, but not too much. Aging here and there. Aging everywhere. We're in the part of the course you can call lifestyle. Last time we did the exercise. How many of you did the exercise? What did you do? Yoga? How was it? Who else? What did you do?
I went for a run.
How was it?
Hard.
Yeah. Who did something different? What?
I lifted weights.
What?
I lifted weights.
Yeah. How was it?
It was good.
Was it the first time?
No.
Extra weights.
No, it's things I used to do and kind of stopped.
Oh, you stopped and now you're revitalizing.
Yeah.
Yeah, I was in the pool and I met someone. I met one of you, and you said, "I'm here because of your course." I don't know if that's true, but it was very nice to hear. So, anyway, so that was your exercise. If you didn't do it, you still have a chance to do it this week. Yeah. Get your calendar, put exercise. And now I want to switch to nutrition. So if we think that the elephant of lifestyle has 4 legs, one of them is exercise, another one is nutrition. Or maybe let's say movement and nourishing. Giving our body good stuff beyond nutrition. And then there's other 2 legs, sleep, let's call it rest, and emotional well-being, let's call it connection, meaning, passion. So today, nutrition. So it's a topic that's hard to study in human beings because people are liars and unruly organisms. That is to say, if you give them a questionnaire, what did you eat last year, every month, it's very unreliable. The data sucks. In order to get a controlled experiment, you need to put people in a metabolic ward of a hospital and monitor exactly what they eat, which limits it to low numbers. So just to give you an example, there's the best study. There's a few good studies like that. There's the epidemiological study in the wild. The best one is considered, one of the best one is on Mediterranean diet called Predimed in Spain. And they took several thousand people with the risk of cardiovascular disease. And they randomized them into 3 groups. One group got a liter of olive oil every week. Another group got some nuts, like walnuts and stuff like that. And another group just had instructions to eat Mediterranean diet, let's say. And they had to dramatically stop because the people in the control arm got 30% more heart attacks. It's a lot. And from there you hear that Mediterranean diet is good. You know Mediterranean diet? Olive oil, grains, meat, protein from chicken, fish, hummus. We're in a good place on earth for Mediterranean diet. But even this study has a criticism. Can anybody guess what the criticism is? It's kind of subtle. The ones in the oil and the nut arm, there was an experimenter coming every week to bring them the oil and the nuts. And so they had more interactions with the experimenter. And there's something called performance bias. When you have somebody caring about what you're eating, you eat better. Just because of that. It's like a placebo, you can say. So it's hard to study. Anyway, what do we know? So we don't know, I guess. We can know more. But in general, I'll show you some evidence the way the consensus is among the researchers now is that, I also want to say, nutrition is very emotional. So it's connected to things like diet wars. Is it better low carb, low fat, keto, right? And a lot of discussion that's. It turns out that it doesn't really matter so much what you eat, with some caveats. What's important is that you're not overnourished or undernourished, that you have enough lean mass, which is muscle, and that you avoid metabolic syndrome. I'll tell you about. So, not over or undernourished. What do I mean by that? I mean, you should eat not too much and not too little, but how much? So the key kind of graph is, this is what I'm going to tell you now is true for a population, not necessarily for an individual, because people have different set points, as I'll discuss, and also different ethnicities. So if you come from East Asia or South Asia, the healthiest point is leaner than if you come from Europe. So the measure you have is what's called BMI, body mass index, which is your weight divided by your height squared. Why this weird measure? Why not weight divided by volume, density, or something like that? Does anybody know?
Easier to measure?
Well, you can measure weight and height and take weight divided by height cubed. That will give you density. So it turns out that weight goes with height squared on average. So this is like deviation from the average, you can say. Another way to think about this is like this measures width. Anyway, here's BMI. Here's 20. Here's 30. Just for, if you look at me, I'm 185, weigh 90 kilo. My BMI is around 26. You can see, okay. My daughter is 14. But for kids, it's different. Kids are supposed to be thin. And here I'm going to put here the hazard ratio, the risk of death in a given year, where 1 is, let's say, the best point, and 2 and 4. Do you remember? I don't remember if I told you this. Hazard ratio of 2 means you have twice the chance to die. And since the risk of death doubles every 8 years, that's like translated to 8 years of life. So hazard ratio of 4 is 16 years of life. 2 doublings. So the graph looks like this. So this is this region here above 30, that's called obesity. And here's extreme obesity. So somewhere around 25 is the optimal. Again, for Europeans, not for in East Asia, South Asia, it's more shifted here. So it's not good on average to be low BMI or high BMI. For women, it's a little bit shifted to, the optimum is a little higher. Male, female. And another interesting thing is if you look with age, so older people, let's say 70-year-olds, compared to the best hazard of 70-year-olds, are shifted to higher, not 30, but higher BMI, so that if you're thin and old, it's not so good.
Also, older people get fat.
And older people get fat. So we'll talk about all this stuff, right? Older people tend to gain weight. There's like you gain weight after 50, but you also lose weight because of muscle wasting. It's complicated what happens. Yeah.
Shouldn't it like be reaching to infinity on the left?
To infinity?
Yeah,
Like if you.
on the left, not like my left, no.
Oh yeah, got it.
Like
Yeah, got it. Yeah.
Way too early.
Yeah, right. So like if you go down to zero, it's you can't be alive with zero.
Yeah,
Oh, yeah.
but also like
Yeah, good point. Yeah.
Like for adults, a BMI of under 15 is as dangerous.
Yeah.
Not
So I just want to let me check it out. With, my graphs here in my lecture notes. You're going to see the lecture notes if you want. My graphs go down to 15. Yeah, it's like around hazard ratio 2 at 15. Let's see. I don't have data below that in the graph. Yeah. So now just an important caveat, as I said, the BMI is one number, but your body composition is much more sophisticated. So if you do a DEXA scan, a low energy X-ray scan, you can see how much fat and muscle you have, and how fat is distributed, etc. So this doesn't take into account how much muscle and fat you have. So you can have high BMI with a lot of muscle, right? It's a lot. So this is like for an average over the population. So, so we don't want to be overnourished or undernourished. Certainly not a lot of fat mass. And that means we need to control the amount of calories we eat, because it's like, as I'll describe to you a little bit kind of conceptually, mathematically, how our weight depends. If you eat more than you spend, if you eat more calories than you spend, you're going to grow in weight. So we need to think of ways to, so this is either counting calories or eating specific things, or seeing when you eat. So these are three strategies that are interesting to talk about, also in terms of longevity, that we'll discuss. Okay, enough lean mass. We said lean mass. We said strength training and protein. You need to eat protein about 1 gram per kilogram, more or less, something like that. Fine. The rest of what you eat, so if you look at food, it has these, you remember the pyramid of carbohydrates, protein, fat, the main constituents, and actually the fourth one, alcohol, is also considered a major component. Alcohol has no benefits. It's like thought that the optimum is 0. Of course, there's social benefits, etc. And the rest, fat, carbs, it doesn't matter, except in specific situations where you're sick, like if you have type 2 diabetes and you have to treat yourself, then going on a ketogenic diet or something like that is very good. But for healthy people, it doesn't matter so much. Carbs, fat, just enough you get enough protein and not too much calorie, not too little calories, you're good. And then one caveat is you want to avoid ultra-processed foods. Now I'm telling you, but then I'll show you a reason why. What's the problem with ultra-processed foods? You want to avoid toxins like mercury that appears if in some tuna. If you eat tons of tuna, there's also all kind of plastic stuff. There's a whole field of toxins, air pollution, etc. And you want to have enough vitamins and minerals. This is clear. So it's not that complicated, except the part of Goldilocks having the right amount of calories. That's requires some thought. And so we have three principles: not overnourished or undernourished, enough lean mass, which means enough protein, and what's this metabolic syndrome? So this is something extremely common that rises with age, and it's an imbalance that is a step in the way to diabetes and to heart disease together. So this is metabolic syndrome is almost always appears before you get the major killers. We need to avoid metabolic syndrome, which has three of five criteria. So you want to avoid, for instance, having blood sugar over 100. What's going on with blood sugar? So it's really interesting. The food we eat you can say gets converted into amino acids and glucose. That's the sugar that our brain uses, our muscles use for energy. And it's great. The thing is that it's under very, very strong control. So when you eat it, the body tries a lot, very, very hard, not to get it so this 100. So if it's controlled so tightly, you guys have, let's say, healthy people have around 90, something like that. 90 is about 5 millimolar. It's about 1 teaspoon of sugar in your bloodstream, 5 grams in your bloodstream. If you go to 120, that's not so much more, right? 20% more. You diagnosed with type 2 diabetes. The glucose is toxic at high levels. It starts sticking to proteins chemically, covalently, and that causes damage to your body. The main part that gets damaged are your blood vessels, the pipes that carry the blood. That causes problems all over the body. You have, like say, the blood vessels in the eye get damaged, you have blindness. The blood vessels in the feet get damaged, and you get these diabetic wounds that can't heal, and then you have amputations. The blood vessels in the kidneys, we filter the blood, get damaged, and you have this kidney disease, dementia. It's terrible. That's called type 2 diabetes. So you want to keep it below 120. If you go above 100, it's called pre-diabetes. It's a step towards diabetes. What is going on here? The body has a great feedback loop for controlling glucose. Why does it fail, and what's going on? Yeah.
I just wanted to double check. You are talking about fasting levels of glucose, not
Yeah,
after
thanks.
fast.
Yeah. Good point. So fasting, thank you. So when you do, maybe you notice, and when you do a blood test in Kupakol, when you go to do a blood test, they tell you to come in the morning and not to eat 8 hours before, because the sugar concentration in the blood here is around 90, let's say, when you're fasting, and here you eat a meal, or actually, let's say you drink 75 grams of glucose in a disgusting bottle for the glucose oral tolerance test that challenges your body to see if you are prone to diabetes. And everyone who got pregnant here knows that it's a test you do for pregnancy, because pregnancy has a risk of gestational diabetes. So you drink your glucose or eat a meal, and it goes up. It can go up to, I don't know, 150, let's say. Then it goes down after 2 hours. So you do a blood test here, here. If it's above 120 or stays higher than something after 2 hours, that's a criteria for having diabetes. So either the steady state or the challenge test. Anyway, why do you get more and more of this when you get old, etc.? One thing is that if you have a lot of fat in our bodies are built to store fat. We can store 90,000 calories of fat in our body or something like that. We can go for almost a month without eating. It has weeks of energy we carry around. That's great. It's obviously good for survival. And the best place to store fat is under the skin. But it has a finite capacity. You don't make the new fat cells. They just grow until they're 1,000 times in volume compared to other cells. And then you still want to store fat. So the body starts storing fat inside. Where? Inside the muscle, inside the liver, fatty liver, inside the pancreas. And when the body senses fat inside itself, it usually thinks something's wrong and starts inflammation. Just like in aging, it's a kind of chronic inflammation. And chronic inflammation is very bad. It's bad for cancer. So people with obesity have lots of kind of cancer going up. It's bad for inflammation has this cool circuit where if inflammation is really from a virus or something, it makes sure that your body doesn't store the glucose but puts it in the blood so your immune system can fight. And it does it by a trick called insulin resistance. It makes the hormone that disposes of glucose less effective for a while. Glucose stays in the blood. But when you get this inflammation, the same thing happens, and now glucose stays in the blood and rises. So basically, being fat, having obesity, you get insulin resistance, high glucose. Okay, that's there's your waist circumference should be less than 102 centimeters or 88 centimeters if you're a woman. Waist circumference is a measure of this visceral fat, basically. If you have high waist circumference, probably means fat is being stored inside your body. Not so good. You need to have triglycerides, which is fat in your blood, below some threshold. You need another kind of lipid, and you need low blood pressure. So I'll put it like this. These are, I said, the conditions for metabolic syndrome, right? The conditions is HDL is low and blood pressure is high. So if you have 3 out of these 5, it's considered to be a step towards problems. Now, I told you that the high glucose causes problems with your blood vessels. Damage to the blood vessels causes these plaques to form in the blood vessels that can constrict the blood vessel, and then there's no oxygen coming. Let's say if it's to the heart, that area dies, that's called a heart attack. Or if it's to the brain, it's called a stroke. So that's why one of the main reasons why you have this all-cause mortality going up here with the fat. Yeah.
Well, I do also have a lot of old people being very thin on the other end.
Old people?
I think like maybe in very old age. So
Yeah, so there's there's a wasting phenomenon. With one of the problems with old age is loss of muscles and sometimes also fat, and that makes you so there is a sweet spot with weight. If you have too much you get all these problems. If you have too little, it's also a problem because your body is very fragile. Doesn't have the energy stores to basically, like, infections are much worse and falls are much worse. And
Kind
things.
of because you lose muscle, or
So part of it is losing muscle. Part of it is, I'll show you less appetite that we want to understand, right? What happens with age. And so. Okay, this is like a maybe depressing topic, but I just want to talk about the major diseases we have in our society: heart attacks, cancer, diabetes, and neurodegeneration. A lot of them are linked to this metabolic syndrome, and that's why I think nutrition, that's the most important thing I would say for nutrition and health to know about. Any questions about this? Recipes maybe?
Do we need to fast from time to time?
Okay, so let's talk about fasting and stuff like that. Predimed, metabolic syndrome, BMI, visceral fat. Okay, perfect. So how do we control our calories? As I said, there's 3 approaches. One of them is really, really famous for aging research. It's called calorie restriction. And it's basically starving yourself. It's like eating 20 to 40% less than you would. So like if you take mice, they eat some amount, you restrict them to have, let's say, 30% less. And it was discovered about 100 years ago that this makes animals live longer. So across the tree of life, restricting calories, so let's say 20 to 40%, increases lifespan. I want to say increases lifespan in the lab or in controlled conditions, because the animals are thin and their immune system isn't great. So I would guess that in the wild it won't increase their lifespan. But in the lab it does. By how much? So in general, if you take different creatures and this is their lifespan, let's say this is maybe worms, this is maybe flies, this is mice, monkeys, humans, percent lifespan extension. So you can get like, I don't know, you can get, let's say, a 10% extension for mice or something like that, and maybe, let's say, a 50% extension for worms. And in monkeys, there's one experiment that extended and one that didn't. I'll tell you about soon. And it's not clear what happens in humans. But if you extrapolate down, it's probably a year. And the one place on Earth where people think there is a kind of a caloric restriction experiment in humans, it's a natural experiment, is in a Japanese island called Okinawa, where naturally they had a problem with nutrition. They ate seaweed and sea creatures, and they had systematically kind of caloric restriction, traditional. Now there's like McDonald's and everything, it's everywhere else. It's estimated that they gained a year or something of lifespan. There's some claim like that. Of course, very problematic, because if you know the history of Japan, the people who lived in that century had a lot of other issues.
So why is that?
Why is what?
Like that worms get like
Why is it a reducing function of lifespan? Right? Why is there a diminishing, not diminishing, but the longer you live, why does caloric restriction act less? So we need to understand what it does. But anyway, this is a graph I collected for you. This was suggested by a researcher called Michael Ringel. And there's a lot of scatter around it, but that's generally the trend. A short-lived organism, it's easier to extend their lifespan. It's, in general, an unsolved problem, how to map experiments from mice to humans. If we knew how to do that, we would have a lot of information. So what does caloric restriction do in our trucks, houses, and garbage model? There's the threshold, there's the noise. What does caloric restriction affect? The houses? Does it make less houses, more trucks, higher threshold, lower noise?
How does it shift the survival pattern?
That's so the way we can know in this course is look at the survival curve shape. So this is survival, age. Start from 100% survival, and this is, let's say, mice. This is 50%. And now you do caloric restriction. Let's see something like this. And you look at the median, and you can also look at the steepness. So this steepness and median tell us what's being affected, because if you affect the trucks, you become steeper, 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 and not steeper. Scaling. So this is, in this model of humans, there's only one thing you can change that makes the graph move parallel to itself. Age divided by the 50% age, 100%. So now the 50% age is at 1, because I normalize time by the 50% point. And caloric restriction just falls on the same graph. If we would have changed the trucks, it would have become steeper. If we had increased the threshold, it would become steeper. If we had reduced the noise, it would become steeper. The only thing that can explain the observed shape, which is moving parallel to itself in the following way, if you increase median lifespan by 10%, you also increase the maximum lifespan by 10%, everything by 10%, is that it's affecting the houses. Now, what about the houses is affecting? So what is affecting about the houses, there's a rate of building the houses. That's I'll put in here a little crane, like we see all around us at Weizmann Institute building the houses, right? And I'll put here a little person inside the house that's cooking and stuff and throwing the onion peels into the garbage. So there's two factors, how quickly we build houses and how much garbage each house makes. Yeah? And you can tell the difference between them by doing this caloric restriction in the middle of life and seeing whether the death hazard jumps or just changes slope. If you build houses slower, the slope changes. If each house starts making less garbage, you immediately gain the benefits. And it's that. What happens with caloric restriction, it changes how much garbage each house makes, which is to say that when you're starving, you reduce, recycle, reuse. Makes sense, right? And this phenomenon of scaling happens in all these organisms, in mice, worms, flies. It's in all of them, and in all of them we also know a lot about the molecular pathways. And the story is very interesting. It has to do with a trade-off that all living organisms have, which is, it's like a trade-off between if food is there to reproduce, and if food is not there, if you reproduce, your offspring are going to die. So instead, you need to wait. and hope that food will come. In order to wait and hope that food will come, you turn on repair strategies. You reduce, reuse, recycle. And the way that's done is by a particular molecular switch that's found in cells from yeast to mice to humans. That's like a food sensor in the cell. It measures amino acids and sugars and decides whether to make biomass or to stop making biomass and instead recycle biomass. Just a switch like that. And caloric restriction plays on that switch. And that switch is inside the houses. That it's called, I'm just giving you the biological name, mTOR and IGF-1. These famous components of the cell tell the cell, the worm, whether it's time to starve and wait. In the book Siddhartha by Hermann Hesse, Buddha has been in the forest for 20 years, and now he had enough of it and he comes to the city. And he sees other hungry men come to the city, and they're so hungry that they find the first job they can in the port, loading stuff, and that's their life. They're going to be loading stuff on ships. But he says, I learned in the forest. I learned how to meditate, I learned how to wait, I learned how to starve. That's my skills. So he sits and watches and observes the city until he sees this wealthy merchant, blah, 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 and gets into a better life. So same thing the worms, the flies, the mice were trying to do. Wait, starve, meditate, then go for it, reproduce. Let that be a lesson for all of us. Okay. Do you know this book, Siddhartha by Hermann Hesse? How many people read it? It's really classic. Okay, so that's how we can, from our model, understand. And of course, there are drugs we're going to talk about in the third part of the course, anti-aging interventions that target, reduce mTOR, for example, activity mimicking starvation or mimicking exercise, etc. So you don't have to lift weights and go to the pool. Maybe someday you'll get a pill to do that for you. Okay, I hope that was amusing for you. Now, in this monkey thing, what does it mean one experiment worked and one experiment didn't? What's going on? So these are 20-year experiments. Highly skilled researchers wanted to know if caloric restriction works on monkeys, so we can know if it's fine for people.
Which monkeys?
Yeah. I don't remember. Rhesus, macaque, I don't remember which one. Sorry. Probably somebody can tell me. So there was one in NIH and another one in Wisconsin, and one had the paper was caloric restriction extends mice life in primates, and then the next one after a few years, caloric restriction does not extend. What's going on? So in a beautiful story of scientific friendship, they got together, they analyzed their protocols, and they published a paper together that explains it, and it's very relevant to us. The difference actually was an experiment they didn't plan, but it's very relevant to us. The difference was this: in one of them, they gave the mice, so there was control mice that could eat as much as they could, and monkeys, and the caloric restriction. Thank you. The caloric restriction mice that had limited food, and in one experiment, they give them basically commercial monkey food, which is junk food, processed food. 28% of it was sugar. The other one, they had a veterinarian dietitian make the mouse food out of whole components, just like you should buy cucumbers, tomatoes, flour, whatever, and make it, right? Processed food, as I'll tell you, is not a good idea. And can you guess what happened? Why don't you pair with each other and guess what was the results in the junk food arm and in the artisanal bread arm? Turn to someone and talk to them. Here, here's your partner. introduce yourself, say hi. Find out their name, her name. You know? Who has a guess? In which one of them did caloric restriction show a lifespan extension? Huh? Who thinks junk food? Who thinks whole food? Okay, so the answer is the junk food arm. The caloric restriction showed a lifespan benefit. In the whole food arm, caloric restriction was the same as the controls. The lifespan. The lifespan was it. Because the junk food arm, the control monkeys became obese, diabetic, and had cancer. So what's going on here? This is very important for us. If you're eating junk food, caloric restriction is good for you. But if you're already eating it as a salad bar, it's not good for you. You're doing enough. Did I explain myself? Event? Yeah? Got it? Okay. Yeah.
If they control the amount of junk food, but not calories, like they could have as much as they want of, healthy foods, and then you give them, a scale of junk food.
You're asking, should you control the composition, junk food or calories?
Yeah.
So I'll talk soon. Explain to you why. When you eat ultra-processed food, you tend to eat more calories.
Yeah, but you can, eat a lot of olive oil and avocado.
Yeah. Okay. And so the question is, junk versus non-junk, same amount of calories. So that experiment was done in humans in a hospital ward, and there was more weight gain on the junk food arm, same amount of calories.
Yeah. But I'm saying, do they show like the obesity? I don't know if a creature overeats significantly, but whole foods, but like.
If you shove whole food down its throat, despite the fact that it's satiating, what's going to happen?
I can throw up.
Okay. So I'll leave it to your imagination. Okay, great. So I want to, after the break, to talk about how is it that our weight is fixed? Because we eat 1 million calories a year. 1 million calories a year. Why is it that most of us stay more or less the same weight? I mean, not everyone, but within a few kilos for decades. And then what happens when we age? So that question of the weight set point, I think, is very beautiful. So we'll take a break now. It's 3 and come back at, it's 2:59. We'll come back at 3:11. Okay? So in the break, I was asked a very interesting question. Why is it that longer you live, the less percent extension by caloric restriction? So one possibility is that evolution is, of course, tuning these things. So if you compare humans to mice, so mice, if you starve them for a couple of days, they'll die. They have very little ability to store energy. And humans, as I said, we have a lot of storage. So also, if you think of a season that has, let's say, there's a season with low food that lasts 3 months. 3 months is like 10% of the mouse lifespan. But 3 months for human beings, it's not 10% of our lifespan. So if we built, let's say, to reduce mTOR, extend our life by 3 months, it will be much, much less for a human being than for a mouse. And so all these considerations could make it that animals that are close to the elephant verdicts, resistant to starvation, are also this particular wait, meditate, and starve strategy doesn't have to be as extensive as for worms or mice, which can't resist starvation. So that's one possibility. It's evolutionary tuning. But maybe there's a deeper reason. But we want to know that we don't know, but we want to know this graph. You can say for all kind of different lifespan extension strategies so that we can extrapolate what's likely to work for us. This like open field for understanding. Open, which means not understood. Okay, so I want to talk about the weight set point. So I wrote a little song. Have you ever wondered why your weight stays nearly constant? Give or take some kilos, over decades it's the same. Of course there are exceptions when we really fluctuate. But after all it seems, there's a set point for our weight. So if you want to know the answer, and you have a curious mind, let me take you by the hand and walk you through the leptin circuit. I'll show you something that will help you understand. Ready? Okay, so we eat, we exercise, we get sick, we don't eat so much, then we eat more, we eat the holidays, we eat a lot, then we eat. So what maintains our weight? And what happens during aging? So to understand that, we need to understand how the body maintains the weight set point. Feedback control of weight. And when I say weight, I'm actually going to talk today about fat mass, because what sets lean mass is still kind of mysterious. What is the weight set point? So the way this works is we have our feeding behavior. Maybe I should start to say, it's a kind of feedback loop between the brain and the fat. The brain controls our feeding behavior, which controls our caloric input. And that makes fat mass grow. Fat used to be thought of as just a boring energy storage depot, but the discovery of hormones like leptin that regulate feeding upgraded its status into a smart organ that talks with the brain, the seat of intelligence. Fat produces the hormone leptin. So the hormone means a molecule made by one organ, goes into the blood and talks with a distant organ. In this case, the brain. And leptin causes the brain to feel full, you can say. Stop seeking food. Okay, that's the feedback loop. There's another little detail that eating increases the rate of leptin secretion. So if you starve for a while, you have less leptin and therefore more eating, you can say. But that's just a detail. Okay. This is a feedback loop. I want to teach you in general how to analyze feedback loops in biology and get some pretty cool observations without math, but with graphical analysis. And it's nice thing about it is also you don't need to know exactly the functions. They could be like this, like this, like this. You can get a lot out of the graphics analysis. It's very general. So what we're going to do when we think about this, so of course, if you eat a lot, you gain fat mass, then you eat less. Some people might say, wait, but we know people who are obese, they eat more. They have a lot of fat and they eat more. So what's going on here? Turns out that people who are obese have leptin resistance and their leptin doesn't work as well. It's a different reason. Okay, but so we need to analyze this. So I'm going to break it down into two arms of the feedback. The first one is eating gets converted to fat. And then I'm going to talk about how fat stops eating. Okay, so basically, right, it's a feedback loop like this. Eating increases fat, fat decreases eating. So I'm going to separate them into two arms. This is what turns this class from just a nutrition class into a systems aging class. So check it out. I'm going to draw here. I'm going to put how much food intake. For now, let's call it in grams. Later we'll talk calories. And here is fat. That's percent of your body that's fat. So of course, when I eat, I have more fat. And when you do experiments on rodents, for example, you get, so what I'm going to do, I'm going to clamp the food. Suppose somehow I'm going to program you to eat this much food per day for a long time, and look at your steady state fat. Right? So I'm holding. So when the trick in feedback loops is I force this, and I see what happens to this at steady state. So of course I'm going to get fatter, fatter, fatter. Where do I reach? And that line looks like this. The more I eat, the more fat. There's a minimum amount of food which is required. So you have your basal metabolic rate. You have your lean mass cost and your fat cost. So at a certain minimum, there's a minimum amount of food required for life. And then the more you eat, the more you can spare for fat. Make sense? Yeah.
What here is like per meal and what is for average?
Let's say food intake grams per day. Is that what you're asking?
Yeah, and over there in the feedback loop, when you do caloric input makes fat or mass, it's like after the meal because.
Yeah, this here takes weeks for the fat to grow, and this part here takes hours.
So when we analyze this it's like per day the feeding behavior.
Yeah, let's say here it's a good point. I mean, I can analyze feeding moment to moment. So I just ate an apple. What am I going to eat next? So not on that level. Not also a whole year, but day by day. That's the level. Okay? Okay. So, and then I want to do the fat inhibits eating. So I'm going to clamp fat. Let's say I fed an animal this much. It's going to get to this fat level. And now I'm going to see how much it's going to eat on the next day. So I clamp fat and I see how much it's going to eat. And that line looks like this. The fatter you are, the more leptin, the less eating. So it's a reducing line. And it looks something like this, experimentally. So the more fat, the less eating because of the leptin. And these two lines meet at this point. And this is the weight set point. So at this point, your fat level makes you eat an amount that supports that fat level. Okay? Now, I'm going to do something like this. Now I'm going to start exercising. I want to analyze what happens when I start exercising, like you did. By the way, this line here is called the appetite line, because it's like the amount of fat makes leptin. Leptin goes to the brain and reduces your appetite, your food-seeking behavior.
But it seems that like fat people has more appetite than.
Yeah, so I said before, fat people, obese, have leptin resistance. Actually, let's start with obese people. Why not? So I just want to say here, this is Umax. This is basically a maximum amount you can eat, stomach maximum. And when the stomach is stretched out, it tells the brain, I can't eat anymore. Also releases hormones like GLP-1, the famous GLP-1, Ozempic. It tells you, stop eating. Okay, so that's the maximum. Okay. When you're obese, what happens is that leptin is less effective. So for a given amount of fat, you have more appetite. So this is what happens when you're obese.
Maybe also like the stomach maximum is like big.
Yeah, it could be bigger if you. Good point. Yeah, if now you like get used to eating a lot, your stomach maximum. So this is also pushed. Great. What happened to the weight set point? Where did it move? In which direction? Higher fat and more eating. Right? More eating, more fat. Just like you said. Okay. Now let's talk about exercise. I burn more calories every day. Okay? I also build some muscle, and muscle just by itself burns calories even when I'm sitting in a class. Which line is affected by exercise? Why don't you turn to the person sitting next to you and try to think which line here is affected by exercise, in which direction does it move, and what happens to the set point? Okay, I'll give you a minute to discuss this. You don't. You know the answer? So tell them. You know? Which line? Which direction? And what's going to happen to the set point? In what sense? Well, are you going to eat more or less? Check it out. Look at it. Yeah, eat more. Yeah, you're right. Okay, who knows the answer? Who knows the answer? Itzar, come. I want you to draw. Come here. Come, and let's give him a round of applause. Okay. It's okay, if it's wrong, it's okay. We still get applause. Okay, let's guarantee him applause after he drops, okay? Let's practice while he comes in. Let's give him 10 seconds of enthusiastic applause. Woo! Okay. Here's the exercise line. Okay. It's okay. The risks are low. What's going to happen to the? Which line is going to move?
I'm going to assume that's the energy line.
Yeah, energy line.
Yeah,
I
I'm going to
agree.
assume that the base metabolic rate rises.
Right. Correct.
generally.
Yeah.
I'm going to also assume that the lean mass cost will rise.
Okay.
Probably have more lean mass fixed.
Yeah.
The fact, that's the question.
Let's imagine it doesn't. So what's going to happen?
Whether it goes up or down again.
Let's say it doesn't
Say it
change.
doesn't.
So
Depending
just
if you're already- if you're already in
just
shape-
draw it. Draw it. Go ahead. Don't worry. If it's wrong, you still get applause.
Okay. Well, I don't know if the slope will change.
So let's say it doesn't.
Let's say it does.
Yeah. Good. So what happened to the weight set point? Can you
Well,
draw
I'm
it?
assuming it. Well,
Yeah.
it's-
Okay. So
it's
what?
not very difficult.
So in real life, so what does this mean for eating? Is eating going to increase or decrease?
Well, it looks like eating is going to increase,
And fat is going to?
decrease.
So the prediction is that if you exercise the mice, they'll eat more and lose weight. And that's exactly what happens. They eat 30% more and they lose 20% weight. Applause for Itzal. Okay, so this is kind of paradoxical, right? You eat more and you lose weight. You eat more and you lose weight. You eat more and you lose weight. So what's going on here? So this shows you that different interventions have different qualitative effects on your set point. If you change the appetite line, this way or this way, the set point slides along this rising line, so you always eat more and gain weight, or eat less and lose weight. It makes sense. But if you move this line, the fixed point slides along a decreasing line, which means that it's paradoxical. If you exercise, you eat more and lose weight. Whereas if you have hypothyroidism, you eat less and gain weight because your energy line is different. So here's a nice thing the graphic analysis can teach us. If we see something wrong with the person or the animal and they're, let's say, eating more and losing weight, we can imagine, oh, it's probably on the energy line. Okay, so that's one interesting thing. Of course, I'm teaching you the kind of math or system analysis, but also we can reflect on, is it true that when you exercise, you eat more? Yeah, it's not? In my experience, it is, but definitely in animals, it's like that, for sure. You give them the wheel, yeah.
I know that people that start running, for example, at the beginning they start losing weight, but after a while their body like adapt to it and they gain the weight they lost again.
Yeah, so gaining weight can be muscle mass. Losing weight, a lot of times in the beginning, losing weight is not fat or muscle, it's water, actually. You change your water balance. And then, of course, in human beings, appetite line also moves because okay, there's other cool ways relevant to our life that you can move the appetite line. For example, as I told you for mice, they gave mice the same amount of calories, but they made the food in different colors and smells. Like very, how do you call it? The food is now more sensory diverse. Would the mice eat more or less? This is called the buffet effect. And which line does it move? Appetite line, because we keep the calories, same calorie. So the buffet effect, maybe the buffet effect wouldn't move your Umax, but it will make you eat more and gain weight. And by the way, same thing with processed food. And that's what happened to the monkeys, and that's what happened to us. The processed food changes our appetite line. Why does it do that? Thanks to capitalism. You want to make money. So you put into food all the things we evolved to crave. Salt, sugar, fat, E122, E124, E127, E3, colors, textures. Oh my God. Because we evolved in a very scarce environment. So now, when I taught this course, I started, or actually we wrote this paper on this thing, which is Ron Bar, I think it's 2020, I had a song saying we don't have a weight loss pill, so we have to like get used to our weight, accept it. It's our way of accepting it. But since then, things have changed in the world. And now we do have a weight loss pill that's quite revolutionary. It could be abused, but it's amazing in that it's really moved the needle on obesity, on cancer, on heart disease. It's amazing drug, actually. People finding more and more good things that it does. No? You don't think so?
We don't know enough.
We don't know enough. Yeah. It's early days, right?
Very skeptical.
You're skeptical.
Yeah.
Healthy
I don't
skepticism.
think it will be good.
You think in the end it won't be good?
I think it's abused.
Abused.
Yeah.
It can be abused, right? If you're like,
Easily abused.
if you're lean and you take it, you get Ozempic face.
Where I come from, 70% of the population is overweight.
Yeah.
70 plus. 40% are obese
Yeah.
in America. Just change your diet.
You mean change your diet? Why do you need a drug? That's what you're saying.
It's a band-aid.
It's a band-aid solution. It doesn't address the root problem. All these points are valid. So, how does it work? Okay, so remember I told you that the gut is built in such a way that when you reach some maximum, it releases not only the muscles of the stomach stretch and you have this signal, it also releases hormones. In fact, there's one hormone, leptin, to make you stop eating. There are like 5 satiety hormones from the gut that are like affecting the brain: GLP-1, ghrelin, orexin. There's all these gut hormones called gut-brain axis. So GLP-1 is a hormone, just like leptin. In fact, it's what people used to think it does, and it does indeed, is it makes the beta cells secrete more insulin. So when you eat sugar, it prepares the body even before the sugar gets to the blood. But it turns out that it also suppresses appetite. It suppresses addiction and stuff like that. So it moves the appetite line. And what it does is it moves the appetite line in this direction. So it's like this. It changes Umax, and you eat less, and your fat reduces. And now I want to talk to you about, people are really worried with this Ozempic because it's like you have to take it lifelong. If you stop, the appetite line moves back. So I want to talk a little bit about these implications of stopping a diet. Like you diet, you lose weight. What happens when you stop? What happens when you stop a diet?
Go back to the original weight.
What else?
Maybe you lost some of the lean mass.
Yeah, you lost during the diet. You lose about, for every 2 kilos of fat, 1 kilo of muscle, something like that. So if you don't exercise, do strength training, stuff like that. So that changes your basal metabolic rate, for example. Not your basal, but your lean mass cost changes your energy line, right? So, in fact, human beings tend after you diet for a long time, you rebound, and your set point ends up higher than it was. So it's not clear what's going to happen with Ozempic. I mean, there's a lot of experiments, but I just want to analyze dynamics a little bit, just for the fun of it. So I'm going to draw the energy line and the diet line, and here's our set point, our food intake and our fat percent. I hope I'm clear with this. Right. And now I'm going to do this. I'm going to make a diet. Now, what's a diet? It's forcing my food intake to be lower than the set point. So by definition, after a while, my fat is going to be exactly what the energy line predicts, because energy line is defined by clamping food and seeing how fat reaches its steady state. So after a while in the diet, I'm here. I'm leaner, grumpier, and eating less. Now, so our fat is a function of time. Used to be F0. I start dieting. It drops, let's say, over a few weeks and reaches a new set point, F diet. My food intake used to be U0. At this point, I force myself to do U diet. That's my diet. Now I'm going to go back to, I'm going to stop the diet. Let's put it this way. I'm going to stop the diet. I open my fridge the next day. What am I going to do? Eat more or less?
Eat more.
Why?
Maybe it's something.
Look at the graph. Why do I eat more?
Because
The appetite line. Okay. I have a little bit of fat. So I just look at the appetite line and say, oh, this is your fat. This is how much you should eat. It's a defense against starvation. If the body doesn't have enough fat, it says, eat, my child. The fridge before you is a wonderland of diverse foods. And you can eat as much as you want, what's called ad libitum in the field, as much as you want. So my food actually overshoots. Higher than it used to be. Overshoots. Wow. And that's exactly what happens to the rodents. Okay, the rodents, you can do all these experiments. Okay, what's going to happen next? Tomorrow.
the fat intake, the fat percentage still doesn't go up, so we still.
Yeah, so the day after tomorrow. So fat's going to go slowly up, right? Because I'm eating so much. And so the next day I'm eating a little bit less. See? Because of the fat. And then go up, up, up. Okay, so I'm going to be eating, so fat's going to go up, 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 back to F0. And my food intake going to go down, 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 down to U0. So you have an overshoot. Incidentally, I won't prove it to you, but I will tell you that if I change not the energy, if I don't do a diet, but I change the appetite line and then I stop, there's no overshoot. The overshoot only when I change my eating because of a separation of time scales where you jump here because the fat line determines how much you eat, and then you slowly, the fat rises, and each day you basically slave to the appetite line of your new fat level. Okay, look. There's no overshoot. This is in mice, but in humans, if you did this for like 6 months, you actually overshoot. And there's different reasons for that. One reason is like with the lean mass. If you lost lean mass, muscles, you're going to have less cost. So the same amount of calories is going to give you more fat. The energy line is shifted. But there's also in humans something called compensatory thermoregulation, which is when you eat less, your body's set point, it's somehow each house is like making less, not each house, each cell has lower metabolic rate. So like the body starts like saving energy. And that lasts a long time. So when you stop the diet, your body's in a set point of wasting less energy, you can say. So there's something in the humans that's different from mice. That's very interesting. Yeah.
Isn't it also at the beginning of the diet that your body like slows down?
Slows down?
Because of like a mechanism of defense, does it lose its energy?
Yeah. Yeah. You're asking, I don't know what happens at the beginning of a diet, but it makes sense.
But like some diets when you start to work out, you gain the weight, like there's the gain of weight when you add the muscle and then like everything like
Balances out.
yeah. And most of the people like become nervous because they're doing a diet but gaining weight and then they stop and
Okay.
then they
Interesting. I don't know all that stuff. I never actually did a diet myself, so I don't know, but it's a whole field of interesting. A lot is not clear, etc. Okay. But I just want to show you how you can kind of analyze the overshoot. And the overshoot happens in all animals, even in flies, etc., when you refeed them. Okay. Now, I want to end by talking about aging, because after all, we're systems biology of aging and longevity. So you want to live longer, what you do with your plate has some relevance, even though exercise is much more relevant. But let's talk about natural aging. So what happens with age to this scheme? One thing that happens with age the basal metabolic rate decreases. Each cell uses less energy. Organs, the costly organs, which are brain and kidney and liver, use less energy, partly because of loss of mass, and partly because they're downregulated. There's reduction in a certain form of thyroid hormone that makes you like hypothyroid a little bit, and reduction in lean mass a lot of times, even though that's not the main reason, all these things. And because metabolic rate decreases, we have an effect that's the anti-Itzhar effect. So Itzhar showed us what happens when you increase your energy expenditure and do exercise. Aging is like this. In general. Let's see, around age 50, you have these changes. You start gaining weight. Also in menopause, you get visceral fat. Some of this is hormonal. Some people think it's a hypothalamus effect that changes your hormone, like testosterone and estrogen, testosterone in men. And you gain weight and you eat less in general. You lose lean mass, you have a danger of losing lean mass, etc. So it's a little bit mysterious, all the factors. I would say that in the garbage truck's house model, one component is, and that's known, is that this chronic low-grade inflammation that you have in your body is having an effect that's similar to chronic illness that has what's called sick behavior, which is reduction in metabolic rate, all kinds of psychological things that make you less active. So it's not exactly the same thing, but it has some similarities. Okay, let's see how we're doing. We did the monkeys, the song, leptin, diet line, set point, exercise, overshoots, leptin resistance, GLP-1, aging, BMR. We're really good at doing very well on time. We have time for a couple of questions. Yeah.
So the graph, the original graph is still in units of grams per something
Oh yeah,
per day.
right, gram per day.
Does the body have a real trustworthy sensor for caloric intake, or is it like or is it rather slow, and the stretch of the stomach is really the best way to
Yeah.
tell?
So how intelligent in the body in figuring out what you're eating in terms of composition?
If you've eaten enough
Yeah.
calories, like
Enough calories, yeah. So the body's, there's a lot of sensors in the body. For example, if you know you're going to eat, the body starts secreting insulin.
digestive enzymes and stuff.
Yeah, so the brain already anticipates. So of course the brain very sophisticated. So the brain, I don't think it's known. At least I don't know how much resolution it has. So for glucose you need the insulin. For fats you need bile acid. For breaking down peptides and stuff you need digestive enzymes. Right? The stomach needs to start. You know the feeling, like you know you're going to eat. You get like your body primes. So I bet you it's pretty sophisticated.
But it's clearly not sensitive enough in terms of caloric intake
look,
having an issue with
we evolved to be in a starved mode, like in a mode that's very low fat and low. So I think this moving of the appetite line is a program thing, which is good in the Stone Age. So in the Stone Age, like the stories usually people talk about and just feels, finally the hunter-gatherer finds a honeycomb of wild bees, right? He fights the wild bees and gets to the honeycomb, and now you have what you can just open the fridge and take the milky. So it's like, of course, this is like super high appetite like food. Like you want to, if you have that, you just want to eat and just store it because it's going to be very, very short lasting and feast. And so all this obesity stuff is thought to be what's called a disease of mismatch, a mismatch between modernity and our evolutionary, whatever it was, our evolutionary heritage, where we were very active. We had no problem with our blood vessels. We had no this overeating thing was very unusual.
and maybe grams per day actually did have a more significant relevance to caloric intake because now like people are confused by okay, obese people have a lower appetite, how? But when you look at appetite only as grams and
Yeah.
mass of food, they're eating maybe less food but more calories
Yeah.
than the amount of grams.
And processed food, so those calories have more of an. So, in fact, when you write down the equation for this line, right, you have d fat dt equals, there's some each gram of food gets translated into fat by this coefficient that tells you how much, let's say if it's pure fat, it's going to be a lot. If it's pure dietary fiber, it's going to be a little. So that's the composition. And then you have here all the costs, like the lean mass costs, and then you have the cost per fat. And at steady state, because this is so slow, you get that fat equals alpha over beta u minus c over beta, and that's this line. This is c over beta, etc. This is okay. So you have this line, and the food composition affects the slope, and the lean mass affects the intercept, and all this kind of thing. So you can figure out what's going on. And of course, the food composition affects the appetite line too. So it's more complicated. That's why I like to draw it in grams and then have those effects writing on it. And in fact, that was a big thing in the paper. Grams, calories, and sometimes it matters, sometimes it doesn't matter. And then the stomach also analyzes, or the intestine analyzes what you eat, and then you have all these hormones, GLP-1, GIP, ghrelin, and they do look at the composition, and they also affect the whole body. So, and also I want to say the body is really, really good at defense against starvation. So this part of the graph, when you have low fat, you push it to Umax. This part is more gradual. There's less defense against overeating, but there is defense against overeating. Defense means a force that returns you. And from an evolutionary point of view, you can imagine that starvation very deadly. Overeating, why is it bad to be very, very, very fat? Yeah, but even let's say you're 20 and the cardiovascular, you're just delicious and animals can eat you. You can't run away. Predation, that's what people think. So it was a tough world out there. You can be eaten. You have to run away from your enemies because 50% of the deaths in the Stone Age apparently were from human on human violence. If you think it's a violent world and things are getting worse.
Human on human, really? There wasn't a lot of humans.
Yeah, but they were so good at killing each other.
And they still were better than
Yeah, if you think things are bad now, it's better now. Most of human history in terms of the way you died or violence. You just find skulls with an axe and broken bones. It's like
But 50%?
50%, yeah. Pretty cool, right? It gives you a perspective on evolution. It's a tough world out there. Those moms, 250,000 years of hominids, like you're able to give birth to a child, you're able to feed the child, you're able to make it come to a maturity age, and you do that for 1,000 generations. It's pretty amazing selection the germline that made us who we are today. This is great. What other question? Yeah.
You said in obesity, the day slept in resistance is
Say again, please.
In obesity, you said the leptin
Resistance.
the resistance.
Leptin resistance. Or maybe, yeah. So there's, what's the question?
Is it higher because they're obese? Or they're obese?
Yeah, is that because they're obese or is it? So if you're born with a rare mutation that makes you leptin resistant, you become very obese. These are babies that can't stop eating and they die unless you able to give them leptin. So when leptin was synthesized in 1980s by Friedman, I know this scientist. I came to visit him in Rockefeller when I was a postdoc, and he had a cage that showed the obese mice. The regular mice. And these obese mice, it turns out, had a mutation in the leptin receptor. That's how he discovered leptin. And they thought that if you inject leptin, it's going to be the anti-diabetic drug. Because it turns out that didn't work because obese people have leptin resistance. It does save the life of the very, very rare babies that are born either without leptin or without leptin receptor. It's life-saving, but not for most people. So I think what happens is that, again, there's all these resistance things like insulin resistance. It's not just a bug, it's a feature in the evolutionary path that if you happen to be in a year where there's a lot of honey, you now want to store it. So you override. So there's a natural kind of feedback. It's some way to turn that knob for a while. But in obesity, something goes wrong and it's stuck there. You become very obese. A lot of inflammation. A lot of inflammation usually causes things like that to happen. So that's why if you inject leptin to obese people, it doesn't work. So that's, very obese people. So that was a disappointing discovery, but that's the way it is. Did I answer your question? No.
What is the chicken right?
I think it's like it's both. It's a self-amplifying. But yeah.
Two questions related. One is leptin signaling constant through life or it's changing when you get older?
I don't know.
And I'm asking this because you see many times old people like at 70, 80, 90, which lose weight
Yeah.
instead of gaining.
For sure.
And I wonder whether
Yeah, that's called wasting or sarcopenia. Wasting. There's loss of muscle for sure, and it's one of the problems of aging. So this is, I think, I look at this as what happened around age 50, 60, 70. And then, so if you look at BMI, which we did, let's say, in Israel, it goes up and then maximizes around 50 and then starts going down. So it's something about old age. If makes you lose muscle, like I said before, muscle mass and muscle strength, and maybe also fat. And also your inner organ, your brain shrinks, your liver shrinks. It's probably time to go, time to retire, time to let the next generation discover the secrets of longevity. As you take your guitar and say, so how can you tell me I've lost weight and I finally fit those jeans? I wish you delicious food made of whole components, lots of free of toxins, lots of minerals and vitamins, together with your exercise regime. Something that makes you, it's nourishing you. Also, who you eat with. Who do you eat with? Someone that like makes your eyes smile. When you eat, to sit down, enjoy the meal, be appreciative. And with these words, we'll meet next week for lecture 9. Aging, aging, aging here and there. Aging, 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 aging everywhere. Aging. Woohoo!